Brüningk. She's a group leader in pediatric oncology, and she has been trained in both experimental biology, physics, computational biology, and she's now leading groundbreaking work at the interface of all of that to hopefully bring some new novelties and useful applications in healthcare. So, Sarah, the floor is yours.
All right, thank you so much for the introduction. Thank you very much for this opportunity to speak to all of you today. This is supposed to be a tutorial, so I hope that maybe we will have some interactions. I did structure this talk as the previous talk, so I will talk for a long time. But please feel free to interrupt if you have questions, if you want to start a discussion on a few points. And also based on this introduction, there is another disclaimer. Yes, I'm not a mathematician, physicist by training, and I will show a lot of things from the applied side of things. Meaning I'll not go in depth here with any form of equations. I know we have a lot of amazing theoretical background people here, and I would love to learn from all of you and take so that I can show you how we can handle this in terms of applications, which is really what we're working for. I'm located at the University of Bern in Untitled, so we're literally in the hospital, and there I'm leading the Center for AI and Radiation Oncology. And this is also some of the applications with pediatric oncology, what I want to bring to all of you today. But before we start with the actual content, the mechanistic learning in math oncology, I just wanted to start a bit with the motivation. I think this is a very general motivation of the hope for personalized medicine. This is not unique to cancer applications. I think this is across the medical domain. Everyone is hoping for this. We want to improve outcomes for our patients by allowing to tailor the treatment to the individual. So pretty much you want to go away from this one-size-fits-all to something that is really tailored to that particular patient, given their specific characteristics that we can obtain from characterization measurements, and that can be imaging, that can be omics, you name it. It is really a large space of data that we now have available about each of our patients. However, the way that treatments have been evolving in clinical practice is through clinical trials, and that is, in the end, an average approach. We find what works best for a certain subset of patients of this population overall. This does not necessarily look at the individual, and this is where the personalized medicine comes in, that we really want to overcome this. And going a step further, what does this mean, personalized medicine? I want to make a treatment decision for this individual, but where does the modeling come in? And I think the biggest hope is really very simplified. Okay, this was not what I was hoping for. Okay, coming in from here, if we have a nice model, yeah, and that can be anything, and I deliberately call this model because it can be math, can be AI, can be both, but you want to make a prediction of the outcome, and again, a very abstract construct here, but the outcome of interest in the context of that particular application. And what we really want to know is if I change things of my feature space, and usually, of course, I can't change the characteristics, but I can change aspects of my treatment, what would this outcome look like in this counterfactual setting? So, modeling speaking, effectively, we just want to have a really well-working tool that we can do a nice counterfactual analysis to make a better informed decision on how I should achieve this personalization of the treatment. Coming now to the data side of things, right? I think we have a lot of applications where there's tremendous and large amounts of data in the real world. In the medical domain, we also have tremendous amounts of data in terms of a lot of information for the individual. There is information on the therapy, the dose, the timing, what it is, and usually patients don't just get one medicine, right? I mean, there are maybe some very rare cases where this is happening. In oncology, certainly this is not a given thing. We have characterization, I already mentioned omics, proteomics, transcriptomics, genomics. But then, of course, there's also imaging, and that can be MRIs, other modalities. We heard a lot about MRI already today. But also histopathology, which is really in the clinical workflows an important type of data used for diagnosing. So it looks good, no? We have all this information available. But the reality of this data, when we go away from these beautiful benchmarks, which we already heard some examples about, is it's not actually that AI or modeling friendly. Because the data, yes, they are acquired inherently longitudinally, meaning I have a sequence on when which point of information comes in. That sequence is determined usually by the treating clinician and potentially the specific hospital's workflows and so on. So there is a sequence to that that is not always deterministic, certainly not regularly sampled either, even if I have the greatest hopes of acquiring my data always at the same time point in terms of follow-up. There's a lot of missingness, and we heard about that yesterday already. Missingness is a real thing. We need to find smarter ways of how we can deal with missing data, because the data is not missing at random. There is usually a good reason why data is available and why it isn't, and the pure presence or absence of a specific data element already tells us a lot about this. Sample size is limited. I think if we were to pool really all the data, maybe this wouldn't be such a problem, but currently as we speak, at least in our domain, it is always hard to get really the large scale of data that we would like to have to really make use of a lot of these beautiful approaches that we have seen. So we need to find a way to handle that. And then last but not least, the cherry on the cake, right? Not only should it be able to handle all of this, it should also be very understandable, so that the treating clinician, who in the end has to make the decision, take the responsibility for this particular patient, can understand what we did here, and that we can have faith in these predictions, that they actually are building on relevant predictors in this context. So this is a difficult setting, and this is now a simplified view, but from my perspective, historically, there have been two sides of things and how we could address this. One I like to call the data-driven domain, and the other one is coming from the knowledge and the understanding, where we are going into the mechanism of the relationship of these different types of data. And if you look about conceptualization, and I want to make it clear here, I'm drawing the extremes on purpose so that we can talk about the same things here. It's about the concept, right? So for knowledge-driven models, because it's a very big class of things that can fall under this term, you try to formulate your current understanding of a given process, let's say the relationship between my data and my outcome measure of interest, in the form of, let's say, equations, rules, right? We try to formulate explicitly what we think our understanding is. In a data-driven approach, we do the other way around. We have data, we have the outcome, and we say, we don't care about this connection, let me just draw it. And that is possible because we're using highly parameterized models in this domain of data-driven approaches, which means we are flexible with respect to the data types that we can digest. But of course, it also comes at the cost that these models are highly parameterized. So I have higher risks of overfitting. I need to make sure that my model actually can generalize, coming down to this question again, did I actually learn something meaningful? What I thought as a human, this model should have learned. And I think this is the nice analogy for the mechanistic models where, yes, potentially we need less data in terms of numbers, but let's also be realistic, we need often very specific data for this. In the oncology domain, we love to show these longitudinal trajectories of tumor volumes, and then now and there something else comes in. It's very difficult to have these data even at a smaller scale. But from the modeling perspective speaking, we can handle very few data points in this context. Complexity, sometimes people like to say, yes, mechanistic models, because they have less parameters. I mean, that is not an argument. Billions of parameters on one side and maybe tens or hundreds on the other side. Yes, maybe they are less parameterized. Are they less complex due to that? That is a very philosophical question. I will just leave it out there to discuss, but certainly there's differences in the numbers of parameters that we need to adjust to the data. And then finally, the last point on transparency. And I think this is also sometimes a misconception when I say, oh yes, my ODE model is perfectly transparent. I can understand what is happening compared to my deep neural network. I think this is the right community to speak to. This is not entirely true, right? It is always an assumption, whatever I put into my mechanistic model. I need to be aware of where do these assumptions stop? How far can I go in this space? And certainly, even a growth rate that we love to use in oncology, growth rate of a tumor, is a complex process that, a lot of things actually contribute to this one parameter, which, yes, I can measure at a certain scale in the end. So these are the two extremes. And of course, we are aware things are not at these two extremes, but we try to make the best of both worlds by combining them. And this is what we call mechanistic learning, at least in this computational oncology domain, where we want to take the best of these two domains and bring them together. So meaning that we want to include priors, mechanistic priors, but also approximate those parts of the solution space where we maybe don't know about the connection. Because if I have a high-dimensional data set, omics characterization again, I do not necessarily know the mechanistic relationships of all 20,000 genes to my outcome of interest, which is probably overall survival of a patient. So going back to this space, what does this mean? Where can we draw connections about this? And this is, of course, at several levels. There can be mechanism-informed choices in terms of how we design our models, how we train them, but also inference from the data directly, and then going towards transparent inference and also learning on real-world data. I know real-world data is also a buzzword, right? But it is a real problem that the data that we have in the real world, in the hospital, is not what we use in typical benchmarks. So, how can we do this? And this is what I want to discuss with you for, I don't know, the next 10 minutes or so. What types of combinations are possible? And I want to make it also clear, this is not an exhaustive list. And this is a very simple picture, but I think it illustrates it quite nicely because it is a parameter space again, right? Where you have your understanding on one axis and the data on the other. And depending on where your specific problem falls in terms of how much do you already know about this relationship, how much and what kind of data do I have, you will fall in one point in this large parameter space. And there is no clear cut. There is no pure mechanistic and pure data-driven models actually in the space. And if you're interested, the QR code goes to a review that we wrote in the context of oncology applications fairly recently. But let's look a little bit into how can we try to structure this? Because I like structure, right? I also think, like probably a lot of people in this room, we like to think in concepts so that we have a nice rule and then we can maybe decide on what should I use in what context. And the first way on how we could combine these knowledge and data-driven models is in sequence, right? So I apply one technique and then the other one after that. But if I can do sequential, of course, I could also do parallel, right? So I can use one of the two approaches for the same purpose. So there is nothing changing in terms of the outcome, but maybe even though I could reach my objective with one way, there is an alternative. I can also combine things, and I think this is much more into what probably everyone thinks about. This is how we should go for. We can combine approaches so that we add to one another, right? So that we achieve an objective, but we have components coming from either the data-driven or the mechanism-driven side of things. Or finally, and I think this is, of course, the most interesting one, intrinsic combinations, where we really intertwine these two approaches. And I'll now go through a little bit in terms of examples from all of this. Again, keep in mind, right, this is not exhaustive. These are just a few sets of examples in the context of oncology applications where this has already been done or where it could be done much more. So let's start with the sequential combinations. And the first part here is knowledge-driven feature selection. And I think we all do that, right? So we wouldn't put something into our model that doesn't make sense. But in the context of oncology, a nice example is, again, and I'm going back to these omics data, it's like, why should I throw in 20,000 samples when I already know there are certain pathways most relevant for this particular problem that I'm interested in? And in the context of the limitations of sample size, it does make sense to pre-select in this context. Easy, right? We all do that. We also deliberately make choices regarding the architecture. Nobody would analyze an image with, let's say, an MLP, right? It makes sense to use architectures that are directed towards the specific data type of interest that we're handling in this context. But then we can go maybe also in the sequential setting a little bit further, right? We can use mechanistic models to derive features from our data. Nice example was, again, this growth rate of a tumor. I can use volumetric trajectories. I can segment these with a unit type architecture. I get volumes, I get growth rates over time, and I can associate that with another endpoint, for example, my outcome of interest. And this can be done at a variety of different scales of complexity. We can really use mechanistic models to extract information or to describe aspects of a process that we will need as an input to a data-driven model. And I'll show us an example later on for this as well. And then, of course, we can also use neural networks to estimate model parameters. So again, we use this approach to estimate the model's parameters so that we can then forward calculate with a mechanistic approach. For example, again, the growth rate example, there's definitely relationships of gene regulatory networks to the growth rate. So if I have expression data, I can use a data-driven approach to associate my growth rate for a specific tumor with inputs such as multi-omics characterization. But then I can use this mechanistic model to predict what is the size going to change in an interval of time. Okay, sequential. That was easy, right? We all do that anyways. Parallel combinations. So the same options in terms of what we achieve. So the goal is the same, but there's different options to achieve that. And I think a very popular example here is neural ODEs. I'm sure a lot of you have heard about it. The idea is really here that we want to consider a neural network as a discretized ODE. So we can solve a complex function with these kind of infinitely approximated layered neural networks in this context. Why would we want to do that? Well, we want to do that in the cases where it's very difficult to actually solve the equation. So we can use this as a nice approximation. Do I learn anything about the mechanism in this context? No. But it will speed up things, it will make things easier, or maybe I can solve an equation I was unable to solve within real, relevant time and computational cost before. So the objective here stays the same. Similar neural networks as surrogate models. I can create synthetic training data with a nice and complex mechanistic model, and I can train a neural network to approximate this system of equations. What this gives me is I can then afterwards, much quicker, generate alternative examples. I can explore this space. So again, the objective here is the same, but we have different ways, and again, it's a speed up, for example, that we gain. And then, of course, there's also the whole aspect of learning equations. And here I'm really not going in depth because I think this is a very active field of research. In the oncology domain, there's really a drive for symbolic regression, so where we want to learn a specific equation given a sparse representation of possible operators and then informing that from the data. Again, this is great because here the objective is the other way around. I would like to learn the mechanism so that I can still describe the same process. But the objective afterwards is, of course, once I know this mechanistic relationship, I can use it to forward project. I can make alternative scenario building afterwards. But I think this is a particularly powerful tool and also very interesting. Still though, it is not giving me anything new beyond what I could have maybe achieved with the data alone, or, well, if I didn't have the mechanism, then I couldn't do that. extrinsic combinations. So this is at a higher level, and post hoc combining things for different objectives. And I think a great example here is the buzzword of digital twins, right? I think digital twins exist across applications. Everyone has their own definitions of it. I will not go too much in detail of how I would define it. I also think it doesn't have to be specific, either mechanistic or data-driven. I would say we should take the best of each of these worlds and put them together. I can use a data-driven contribution to digest my hard-to-structure data. Again, the omics example, right? I should use data-driven modalities in this. But I should also use mechanistic modeling to describe the aspects of this virtual patient that I know very well in terms of the underlying mechanism. Again, the growth of the tumor, right? We have a ton of models that describe this. So the idea here is really to put together different building blocks from different components for one greater objective, which is in this case providing an as comprehensive representation of this patient as possible. Then there's of course complementary post-processing, and that can go either way, right? I can use a mathematical analysis of neural networks, for example, in the context of explainability, and I can also do a data-driven analysis of mathematical solutions. For example, if we have very high numbers of, let's say, drug response profiles longitudinally, I have extracted a number of parameterized profiles from a fit of a mechanistic model. I need to understand the relationships between these parameters. How does it relate to the trajectory overall? And here is a beautiful example where I can combine a time series clustering with an analysis of this parameter space that I obtained. So it is kind of adding on top of each other in this context. And then, of course, intrinsic combination. Here's where it becomes interesting. I couldn't come here without briefly at least mentioning PINs, right? Physics-informed neural networks. Don't even get me when we wrote this review on why someone calls it physics-informed or biology-informed. There's apparently hugely different opinions on that. I called it PINs. The context is here, we constrain our loss to physically, in this context, meaningful differential equation. And by doing that effectively, we can, of course, obtain a better training, right? We train on solutions that are physically meaningful. I constrict my parameter space, and therefore I can optimize more efficiently. At least that's the hope for it. We still need data in this context, but I think it's a really nice and powerful concept on how we can really marry these two concepts together. And I also want to give a shout out to the UPINs, right, Universal Physics-Informed Neural Networks, where we add components, small neural networks again, in this context, where we maybe do not know the full equation that we want to constrain by in this context. Okay, moving on, so constraining the loss function by a mechanistic prior. Of course, if I can constrain the loss, I can also constrain the architecture. Someone came up with the name biology-informed neural networks for it. I don't think that is necessarily conceptually a difference. But here what we mean is constraining the architecture, meaning if I have a gene regulatory network, and a lot of biologists spend lots of time in the lab really trying to figure out who relates and who controls who. We should use that information and this understanding in graph representations when we let them loose on our multiomics data, rather than going in with a fully connected network. Yeah? And this is an example here where they did this, right? So you try to mimic a gene regulatory network at different levels, from the genes to the pathways to the processes. Could also go to transcription factors in this context. So, long story short, you try to constrain the architecture in this context. Can you now combine a biologically informed architecture with a physics-informed loss? Of course, right? Has someone done it? I don't know. But just to give you the idea of what would be possible in this space. And then the last example, and this is a very general one, again, it's a hierarchical approach. Think about the sequential combinations. One model applied after the other. Well, that is good, but it is much better if I actually train this end to end so that I can also propagate uncertainties through this. And this was a very nice paper where they actually did this. nonlinear mixed effect model, so basic architecture in this context. But it was a really nice combination of a mechanistic model and then relating that to the patient-level response in terms of overall survival applications. What you should take away from it is propagating uncertainty to it, using an architecture to really marry different concepts together in this combination. So this was kind of a very quick summary of what types of flavors of mechanistic learning there could be. I think probably here this is a community where everyone does this to some extent, but maybe this also gives you a bit of ideas of what else could be done. And whenever the question comes up, and I think this is something we do very much in the applied space, because we have these constraints, much more maybe than you guys do in the theory, on which one is the right approach here, and how can I combine it given the limitations I have? So what data do I have in terms of size, in terms of what is important after I talk to my clinician, because they always have a very good intuition of what should be important for certain problems. The longitudinal aspects and how I can account for this irregular sampling, and then of course also the other side, the knowledge that I have and what I'm actually trying to achieve, right? And that probably defines very well what type of combination makes the most sense here. And of course, what degree of interpretability is also needed. A sequential approach remains fairly transparent. I can very well control the different components. Explaining a physics-informed network to a clinician, it is going a bit far, but I think they will still like the idea of I still have at least this notion of constraining it to something that I can physically understand and have much more tangible. So here I will stop, because now I will go to an example of what we do in the lab. And I was hoping maybe there are some questions, comments in this context. We saw some examples already previously. Yes?
It reminds me a lot of knowledge gathered or physics gathered machine learning. It's
Yeah.
really nice to see it contextualized like this. Probably, if you're going to get to it, you can ignore my question, but like, what exact mechanistic understanding actually helped you in prediction, and does it only help you in prediction or also in generalization?
It depends on your application, right? I think I will show you an example here where it was really a problem in the data, where I would say if I had all the data in the world, I wouldn't need this combination. But I would answer this question of like, what mechanisms do I use and how do I incorporate it? It really depends on the application that we would like to address. Does that roughly? I mean, maybe we will continue and we'll see, and I hope.
Curiosity, because it's so rare that we have an exact mechanistic understanding and access to all the data. So it helps sometimes in our field. I would say it's like a 10-20% of the cases. So what about your field?
But you used the word exact, right? And I think the notion of having an exact mechanistic understanding in the context of medicine, I dare to say we're far from that, right? I mean, maybe at the very molecular scale, there is a fairly exact approximation of certain processes. But I can tell you, once we go to the macroscopic patient, I think it's not easy to say this is an exact mechanism. I can probably give you a fairly good approximation within a given constraint of assumptions. Again, this example of the growth, right? I know tumors grow longitudinally at a given rate and then they will plateau. That is an established mechanism, I would rather call it in this context. And there are, of course, a lot of these models because the field of data science, let's be realistic, is still fairly young. And before the 2000s, people were already using mechanistic equations also in the context of oncology. So maybe let's have a look at this example. And this is an example from radiotherapy. And I wasn't sure who knows about radiotherapy here, but just to give you an overview, it's a complex workflow. Radiotherapy is actually used about in a third of cancer patients. So it's really a common treatment that is used throughout all age ranges and application ranges in terms of oncology. So it's not specific to one type of tumor. Usually you have this pipeline. You assess the patient, you take an image of this patient and then you actually do the contouring, what we discussed before. You outline the tumor on the image, you outline organs at risk, and you use these to make a specific plan for each individual patient. So in radiotherapy, we are actually already providing a personalized plan for each patient. Then there is a lot of QA, and then there's complex machinery that delivers these treatment plans. And then, of course, there's the follow-up where we want to know how well did we actually do. And I will not go in depth because actually we're running out of time rather quickly. But AI, or let's call it model-driven solutions, can support each of these steps from the diagnosis and the decision for the specific treatment towards a lot of automation in this context, so automated segmentation, automated planning, and also then, of course, the retrospective analysis of follow-up, right? So where we want to see how well did this patient do, how can I relate this to what it did in the first step for the planning so that I can improve for this particular patient. And I wanted to add this slide because this is the ultimate reality. This is what is being done in industry, right? So what are the tools that we physically use in practice that already include some kind of modeling? And to summarize it on the left, first you see the publications, and there is a surge in publication over the last years. It's a lot of focus on automation of processes. And I think yesterday we had this discussion about the agentic AI. This is a great example. We are trying to outsource currently the tasks that are kind of easy. They are just time consuming to be done. So this is a lot on automated contouring of tumors that facilitates tracking, breathing, for example, of the patient during the treatment, registration, and monitoring of these machines. But what we're not actually seeing yet, neither in the clinic really, nor in industry, is the previous part on the very left, right? So which is this one, this retrospective analysis. So really relating to an outcome in this context. And this is what we're particularly interested in. How can we actually make such predictions? And I want to introduce you to the application that we work with quite a lot. It's pediatric diffuse midline glioma, DMG. It's a type of brain tumor, but I think it's also nice to understand it's a rare type of tumor in the brain stem, actually. The brain stem really is the part of the brain that controls the most vital functions, such as breathing. And you can imagine having a tumor in that location is not very good. Also, as the name suggests, it's a diffuse tumor, so that means it's very infiltrative. And taking all of this together, this is a tumor type that really has particularly poor prognosis. It affects young children, and median overall survival is typically below 1 year. There is no curative treatment available, and radiotherapy hence is really an integral part of the management of these patients. It is key for palliation, also gives to some extent some improvements in overall survival. But we're currently treating these patients as we do our adults, because we cannot easily run a clinical trial in pediatric applications. We cannot, and also ethically, we wouldn't want to kind of play on this regard. So here it is even more important, can we provide a good prediction so that I can run a counterfactual to see what potentially could be meaningful to try in this very specific type of population. It is, of course, it's rare, right? But that means small data. That also means that if we want to do something on these types of data, we need to pull data from multiple institutions. And there is no successful standard of care, meaning that patients have actually received a variety of treatments throughout. What we, however, also see is that there is a dynamic adaptation of the treatments, meaning that there is really a close interaction between the different groups in the clinical context. So we're really trying to personalize treatments here already for the individual, but we're doing this pretty much flying blindly. And so what we want to provide here is an estimate of radiotherapy response for these patients. And we're talking about mechanistic learning, right? So let's first have a look briefly at the mechanism of action of radiation. And a patient consists of, molecule cells, then the tumor, microenvironment, the whole patient ecosystem overall. So as we're talking here about the scales from the molecules to the earth, here we're talking from the molecule to the level of the patient. And of course, we can assess the effects of a treatment, in this case radiation, at each of these different scales of complexity. Molecular level, we induce damage to the DNA. That manifests in a response of the cells to that. There is cell cycle arrest. Ideally, there is death, but there is also signaling of these cells, which means at the microenvironmental level, there is then also a response of the system, right? You have immune modulation, you have organs that respond to this as well. And then, of course, there is observations on the macroscopic scale, which is macroscopically the size of the tumor, very macroscopically life or death, overall survival of these patients. But of course, there's also concerns regarding the quality of life and the toxicity that we actually induce with these patients. And I think here it's already clear, right? It is a very complex mechanism that we try to describe. And maybe at this level, we have a good mechanistic understanding of what is happening. Maybe at this level, we can approximate a few things with respective simplifications. But it is very difficult to really draw the connection across all of these scales. And more complication is that usually we assess the efficacy of radiation. I just want to mention, radiation is an old treatment field, so we have done this for decades already, but this is assessed also at very different levels in very different biological systems in terms of scale, from the individual cells to the patient level. And ideally, we would like to, of course, marry across these scales. And there's also, that's why I wanted to mention this here as well, an increasing uncertainty in terms of the dose, right? So how much dose is actually reaching that particular part so that I can control for it. Because that's what we're ultimately planning in the end, is what dose do we give to what structure in this patient. So where can we personalize radiotherapy? I already said there is a plan for each patient. Which sounds good. So we outline what we see visibly as the tumor. However, a lot of these tumors, they are infiltrative. So we need an expansion to account for what we cannot see on the image. And that is the so-called clinical target volume, which is effectively an isotropic currently expansion of this volume, so where we think there's microscopic infiltration. And yes, there are a lot of mechanistic models that tell us otherwise, that this is not an isotropic infiltration. But currently there is no clinical tool or reliable enough tool that we could use to actually inform us on how to draw these margins better. Fractionation, meaning that I give a dose of radiation to this tumor. Radiotherapy is not giving as a one-off treatment, but actually we give this over the course of 6 weeks, daily fractions, except for the weekends. And we give this every day the same size of dose. And who tells us that this is a good thing? Is this optimal? There's a huge parameter space of what we could optimize for, the size of the dose, the spacing of these fractions as well. And then finally, the specific prescription of the dose. Currently, we're targeting the tumor homogeneously, even though we know this tumor is not a homogeneous mass of proliferating cells. There's microenvironmental factors, there's gradients. So of course there would be potential to boost specific regions or maybe to spare others, also in favor of healthy structures that are nearby. And how do we assess all of that? So what is our data of interest? And that is magnetic resonance imaging, right? So we use that to, first of all, make an assessment of the patient, draw our diagnosis, then we prescribe a treatment, and again, we use imaging to observe the response in these patients. And we specifically have criteria from the radiology department, response assessment, pediatrics, pediatric neuro-oncology, RAPNO. We're looking at the different contrasts. We draw bidirectional measurements, and yes, it is 2-axis, it is not a segmentation of the whole tumor volume, and then we compare across 2 fixed time points, before the treatment and after. And I can tell you guys, right, the trajectory across 2 points, there's a lot of trajectories I could draw, and I think it would be important to understand in what part of this trajectory we are. Currently, we're not doing that. But there is hope, right? So recently, for both the pediatric and the adult community, there is really, with the help of data-driven tools, a surge in using automated segmentation to facilitate longitudinal tracking, and how could we actually involve AI, and this is usually talking about AI because that's the hype currently, in the context of response assessments. And what this yields us is then we are going towards trajectories, and I'm showing you here 3 different models, 1 manual. Yes, they are not perfect because the DICE score, we will never reach 100%. Does it matter for the trajectory here? I would argue probably not so much, depending on how I assess specifically in this context. And this is just supposed to give you an example of actually what this clinical data looks like. And I think this is also a type of data that is clinically achievable now very soon, because segmentation models are coming to the clinic, and this is coming that we have a trajectory of our tumor over time. But keep in mind, the decision is currently clinically not made only on a trajectory, it is made based on the full image, the MRI, right? So I look at this image. And so if I were able to provide a prediction of my outcome in this space, my doctors would be happy because I could actually use this to say, what is this tumor going to look like in the future? I can make adaptations of my treatment to identify regions at high risk of progression. Or I could use it in the context of a synthetic control. If I have given my patient a specific treatment, I could model what would this patient have looked like in the absence of treatment. And in a setting such as pediatric oncology, where we don't have a control arm, this could be a very powerful tool to actually dissect small benefits, maybe also at the smaller scale at individual patient level, given that these predictions are reliable enough, of course. So how can we achieve this? And this is now this example of this mechanistic modeling. As a PhD student of mine, Daria, she's been working on this for some time. We're showing here kind of the first stage of this project, which is about modeling anatomical tumor growth on MRIs for these particular patients. Diffusion models, I think everyone here knows how a diffusion model works. I'll not go in depth, but I want you to take away that we're using here a guidance towards the size of the tumor. So we predefine the size of the tumor that we would like to achieve in these images. And when we started this was actually still kind of something that was new at the time. So I think it was quite exciting to see, can we actually model growth of these patients? But we didn't want to show just, we can create an image, because yes, that is possible. And I think there's a number of papers out there that also show that. But we actually wanted to quantify the realism of these images in the context of the application that we're after. And that means, how do these images appear to radiologists? How do they relate to the application? Meaning that, do these tumors actually grow in line with how the tumors in the patients are growing if I increase the size of these? So it's about comparison to longitudinal trajectories as well. Data, right? So we need data to train diffusion models, and I'm using here the BRATS data. So we heard a lot about this. It is very hard to get our hands on large-scale data. This is a beautiful data set comprising predominantly adult glioblastoma astrocytoma patients. It's not the type of tumor that we're interested in, which is diffuse midline glioma, but there was a subset of 140 patients, pre-treatment, single time point, all of these available. And so we wanted to train this diffusion model to see, can we abstract the general growth patterns of these tumors? Because this is something that is actually far more complicated as that I could describe it with a mechanistic model at this given scale, given that I have no longitudinal data. We do have, though, and in this particular study, we used a small subset of 13 patients where we had very beautiful longitudinal follow-up, also in the absence of treatment. And this is what we wanted to use for the comparison. There was a big jump to make, though, and that was this one, that GBMs are in a different part of the brain than our brainstem tumors. So we wanted to see how that does actually work out. And these are some examples. I think this was a very early image that we obtained, and we were very happy talking in the cafeteria how well our tumors are growing in the brain. And of course, yes, we can generate for a given slice, I should emphasize, a tumor at a different size. We can look at the anomaly map afterwards, and yes, we can compare that as well. What is nice, though, is yes, I can repeat this process. I can add slightly different noise patterns, and so I get a probability map by stacking up these images. So I can obtain not only one image representation, but we can actually obtain a probability distribution of where are likely regions that will be classified as tumor in these generated images. And what is particularly nice about this is if I stack them back together, I actually end up with a nice homogeneous volume again, which is of course an issue if we have a 2D model. Yes, I would love to use a 3D diffusion model. Unfortunately, we do not have the compute capacities at this point to provide these predictions at the resolution which we would require them at. And so this was kind of a way to go around this. So we can stack two-dimensional growth probability maps afterwards. But how realistic is this, right? So first thing we do is we benchmark with the metrics. So SSIM, peak signal to noise ratio, FID. I think these are metrics we see a lot in these computational papers. And I think we didn't do too badly overall. But what does this actually mean, right? And so here are two examples. Interactive tutorial. Does anyone know which one is real or fake? Both could be real, both could be fake. If we think the left one is real, okay. If we think the right one is real, okay. So I can see there is some hesitation, right? So answer is, okay, one was real, one was fake in this scenario. We did this with a bunch of 5 radiologists and then later on with a larger cohort. Summary was, they could not distinguish this, which was actually for once really nice, right? We had a perfectly balanced set. We had these tumors at a given size. We didn't tell them if they should be larger or smaller. And it was really interesting that they were not able to tell. We should stress though, this is artificial setting for the radiologists as well, if you just see a single slice in this context. What was nice though to see is if I train a unit to do the same task, it does actually better. And when we looked in depth of what was driving these differences, it's actually underlying noise features of this image, which makes sense in hindsight if you think about it, because it's the noising process. Does this mean I now need to go back? And we had a lot of discussion. Should I make sure that my noise levels also mimic what I have in there? I would say actually no, because my endpoint is achieved. My medical doctors were unable to dissect these, so it depends on my application. If I use this as synthetic input to train a model, I should be careful. I should think about this, if this is important, the noise level or not. If it's about defining how the tumor grows, I seem to be okay in this context. And this was, of course, the most important part, and is to validate the longitudinal growth. And this we did again with dice coefficients. I think it's not the perfect metric because I would much rather like something that really looks also at directionality, because I think this was really the strongest point of these predictions. This is the starting image. Prediction says it's going to grow here and here, and actually this is also what we observed. Dice looks good. It is a small data set though, right? 178 slices from 13 patients. But it looks at this point at least good enough that we want to move further with this. So now you may wonder, so mechanistic learning, didn't we talk about that, right? So where is the time, right? I just predicted your beautiful image, apparently kind of realistic in this very limited assessment here, at a fixed size that I predefined. This is not necessarily what I promised you. We wanted to have prediction at a later time point, and ideally also prediction after radiotherapy. And this is where the mechanistic modeling comes in. We only have 10 minutes left, so I think I will skip a few of these slides, but the idea is that we designed here a mechanistic tumor growth model predominantly inspired by spheroids. This is an in vitro system where we can observe at scale how tumor cells respond to different types of treatments. And the model we used here, it is incredibly simple. You just quantify a fraction of cells that is transitioning to a different compartment, which decays away, and we give this model enough flexibility potentially to account for different growth dynamics that would happen in response to these treatments. There's a lot of analysis that has to be done or is being done in terms of which parameters can we actually identify from this. But the nice thing is that we could fit this model to trajectories of spheroids we could fit this model to trajectories of tumor growths. And these are actually low grades. We also did it for high-grade glioma. I'm sorry, it's two different types of plots because it comes from different types of publications to put this together. And eventually we also used it for diffuse midline glioma, and we could actually use the same very simple approximation with this mechanistic ODE model in this context. And of course the application is very nice, and in the interest of, I will skip about these two, but I want to talk about this one, because if we have this mechanistic description, I can actually achieve one of my objectives that I wanted to look into, which is the fractionation. I can simulate alternative fractionation scenarios here. I can change the size, the time between two fractions, and then look into how would the trajectories respond to that. And we can quantify that in terms of patient response, and then here we went to a Kaplan-Meier plot, meaning just we cut off at a given size of the tumor in the end. But it was interesting to see that there were actually subgroups of patients that would, some of them potentially benefit from a larger time between these, and some wouldn't. And I think this also makes perfect sense, because in the clinic we don't do these schedules because there was no other way. This has evolved historically in a trial and error process to what is best for the population level, right? Doesn't mean that within that population there are not subgroups, for some of which it would actually be beneficial to do something else. So, going back to the mechanistic learning approach, and this is where it actually now comes together. So what we did now is that we had our ODE model, and we first of all parameterized this on our volumetric, area, back to area because 2D, on our area-wise trajectories, and then we inform this growth factor in this guided denoising diffusion model based on the output of the fit of this ODE model. And of course, as any model, there's uncertainty to that, there's uncertainty to the data points, and because of the sampling process, it is actually nice that we can also sample here from a distribution of predicted sizes at a data point that was not included in the fit of this model. So is this perfectly there where we want to be? Of course not yet, because we need a certain number of data points currently to parameterize this curve before we can make this prediction. But we looked at it in terms of performance, and yes, we are quantifying this with coefficients of determination, normalized root mean square errors. It was not perfect, but for the purpose that we wanted to look at here, it was good enough, because what we then sampled, in the end, I'm showing you here individual trajectories that can be sampled from this, is again a probability map for this particular tumor, now at a later point in time. And we compare this in here in terms of Hausdorff distance, also in terms of dice, between generation of the true size and the estimated size. Actually, there was no significant difference between this, which is nice, because now we can go actually this extra step, and given I have a certain set of data, and that is still a limitation, we can now make a prediction at a later time point of what this tumor is likely going to look like, and we have validated that it actually also agrees with the region where this particular tumor would grow to. So it looks nice, but how can we actually account for the missing parts still, right? I still need these 4 parameters for this mechanistic model. And this is where I just wanted to leave this to an outlook. This is what we're currently investigating. But of course, there's advanced imaging techniques, such as diffusion imaging. You could actually get cellular densities, and it was previously shown that you could abstract information such as growth rates from these types of assessments. And then coming back to my favorite one, the omics data, right? Because this is important and we should consider it. And we can actually, this is a project that is currently ongoing for Lawrence, where we want to use transcriptomics to predict surviving fractions of cells. And this is one of these parameters that actually characterizes the fraction of cells that will ultimately die following radiotherapy. There is a lot of data actually available in a number of spaces, including here the preclinical space where you have a number of cell lines and then pair that with these quantifications. And with this, I will leave it, and we have a few minutes left for discussion. But I hope I could give you a bit of an applied view of what can be done with combinations of mechanistic models, data-driven approaches, and maybe also motivate some discussion of how we can maybe take some approaches from very different domains, such as the geosciences, and see how we can adapt them to the medical applications, where I think we are mostly constrained by the reality of the data that we currently have. So thank you so much. Hope there is some discussion now. And most important side, I want to thank, of course, my team. Yeah? So this is not just work that I do, this is really a team behind it, and in particular for this presentation, Daria and Eftimis, PhD student and postdoc, working on this particular project. Thank you.
So thank you for this really interesting presentation. Are there any questions?
So, okay. Are there folks using the generative approach to predict tumor progression over time and then check that against progression in the same patient? I'm wondering, is that possible, or?
I mean, this is what we did effectively.
That's what you did, okay.
Right? So we had, for a subset of patients, you have 2 images, and then you validate, does it actually correlate where this patient is progressing to? Yes.
Okay, so you have the temporal connection somehow built into
Yes,
the
but we don't train on temporal data.
Yeah, right.
This is the big difference, and this is something we're looking into now, because, of course, if we had large-scale longitudinal data, we could marry this much better. But I think reality, at least for brain tumors, is that there is a limited number of data points. If you're very lucky, you have maybe 6, 8 upwards of numbers, but we will never have a time series in that regard.
If I understood correctly, so you mentioned quite early on about the radiotherapy planning, and that you have this kind of isotropic expansion of the tumor,
Yes.
which isn't realistic, and now you have these models, and you can not only predict in which direction the tumor would go, but also maybe give a probability map about in which directions and to what extent the tumor would go.
Yes.
And now the contours that you do, these are then inputs into a radiotherapy planning algorithm to give the doses. How do you have concepts for how you could integrate this probability map into the dose plan?
Yes. So there is already the concept of this clinical target volume, and actually this is something we don't want to try it on the patients just yet. I should also stress there is, of course, we're not the only ones working on this. There is an ongoing study which predicted location of recurrence. So they didn't predict the growth of the tumor, but they predicted where the tumor is most likely to recur, and they boost that region with radiation. And they actually could show that this could improve outcomes in terms of progression-free survival for these patients. But so that could be done. But currently, clinically, because we have to follow the standard, right? This is not a thing. But there is certain freedom within the guidelines that if I have a certain size of a margin, I could potentially choose, me being now the clinician, they are free to decide to some extent. They are using their general clinical understanding of how brain tumors grow in order to draw these contours. And currently, this is all they can base it off. And so when we discussed this with our clinical team, they actually quite like the idea. But before we could do this clinically, what we want to do now is actually, first of all, validate. We want to use current CTVs and the current plans and see can we actually reproduce the response with a given plan, and then do this counterfactual setting is if I had a different plan because I have a different target, would that change my response? That is, it is currently what we're working on now, to include the plan as well.
Presumably, because the calculation of the dose is not only dependent on the tumor, but also the patient's anatomy.
Exactly.
Right? And if you had a suspicion it goes in this direction, but it wouldn't impact the other organs, maybe?
Well, the other organs, it will not necessarily impact, right? But because the target you draw where you think there's microscopic infiltration, and you could argue that we assume that where the tumor is likely going to progress, there is also the directionality of the gradient of the infiltration in this context. So in that regard, you're not changing the anatomy because there you have that image. So the calculation would still be the same, but you change your target definition, and yes, that overall changes the plan that is being delivered.
Could you say a little bit more about the parameter estimation in the mechanistic models? You mentioned you're using neural networks, for example, to automate that
Yes.
parameter. Could you say a little bit about that?
So, I mean, in the way that we did it now, it was a fit, right? So we fit this to the volumetric growth curves. But what we're doing now in the spheroids, actually, this is the first level, it's like there we have larger scale data where we have a mapping of transcriptomic information, and I have a mapping of a very limited number of parameters, and we see how we can estimate now these parameters from a transcriptomic profile. And I think if that would work preclinically, this could be something we can see, can we relate this to the parameters we currently extract for patient trajectories and relate it to their transcriptomic profiles. But I couldn't do it at the level of the patient because we don't have the numbers at this point. But the other thing is also to look into association and prediction, right? So I'm fairly sure if we have enough data, we can probably also predict other aspects of this trajectory from the imaging. And the other thing we're now looking as well is the video part of it, right? So we can now generate synthetic data with this along this trajectory. So I can maybe make up for this limitation and then train a different type of data-driven approach there in this context.
Yeah, thank you for the talk. Also, I was looking at your guided diffusion paper. It's really, really nice. I think this is a very promising direction. What are your thoughts on the other way around? So equation learning, you advertise symbolic regression, but do you think symbolic regression is all it takes, or have you thought about it? We have tricks in our field to make it work. Like, what are your thoughts in your field?
Well, it depends on where. I think symbolic regression has a place, and I think one place, again, where I want to try this is actually, again, on the spheroids, right? Because I want to see is there a simpler way of how I could still describe this with a different type of model. But otherwise, I'm very interested also in the whole operator learning, not necessarily for brain tumors alone, but for example, for brain metastasis, to understand better how and where metastasis would spread. Because I also think there is a mechanistic relationship in this context, but there we do not have a good enough, at least, understanding of the mechanistic underpinnings of that at this moment. But yes, in principle, you can turn things around one way or another. I feel a purely mechanistic model in this context might be oversimplifying things. It is a very complex task because you have the whole healthy anatomy in the surrounding as well, which is very important in this context. And I think that is actually very hard to model in that depth mechanistically. All right.
Is there one last question, or should we move it informally to the lunch break? So let's thank again Sarah for this really interesting talk and discussion.